Yunyi Zhu from MIT CSAIL. Today, we will introduce PortaChrome, a portable contact light source for integrated reprogrammable multicolor textures on photochromic objects. This work is done in collaboration with my colleagues, Cedric, Yixiao, Junyi, Angelina, Kyle, Grace, Luca, Michael, and Stephanie. Photochromic material is a type of color-changing material whose color and pattern can be reprogrammed with light. In prior work, we show how we can coat mixed multicolor photochromic material onto a 3D object and use projectors to achieve reprogrammable textures. While this approach achieves high-resolution multicolor results, it requires the user to intentionally place the object into an enclosure and later take it out in order for the color change to take place. This limits the size of the photochromic object to small desktop objects, and the interaction of the color change is associated with. To improve on this aspect, our goal is to integrate the color changing process into the user's everyday interaction. Let's bring our focus to the light source for photochromic material, which is the device that makes the color changing possible. Because of the need for precisely controlled light, prior works, including Color Mod, Photochromeleon, and Chromo Update, all use projectors. However, this does not have to be the case. In fact, since photochromic material requires only light of 4 wavelengths, UV, blue, green, and red, as long as the light source can supply these wavelengths, they will be able to interact and reprogram the multicolor photochromic material to the same extent. To showcase this possibility, we developed PortaChrome, a light source for photochromic material that's portable and flexible. PortaChrome can be rolled, folded, and attached to everyday objects. For example, it can be attached onto a backpack and allows the user to reprogram the back of their t-shirt every time they wear the backpack. As a result, the user can use the t-shirt as a canvas for visualizing the progress of a hike or showcase the user's active minutes. In this case, the user integrates the color-changing process on the t-shirt with the process of wearing the backpack. Next, we discuss how PortaChrome is made. PortaChrome consists of 4 layers, the top being in direct contact with the photochromic object. Starting from the bottom, we have the UV protection layer, which absorbs the UV light and prevents it from leaking into the environment. Going up, we have the RGB and UV LED layers, which contains LEDs that supplies the required wavelength of light. On the top, we have the silicone diffusing layer, which allows the uneven light from the LEDs to form controllable pixels. All 4 layers can be made with Makerspace available tools. We will start with the UV and RGB LED layers. To allow reprogramming the dye, we source our UV LEDs at the wavelength of 365 nanometer required to fully saturate the dye. And we verify the wavelength of RGB LEDs with the absorption spectrum of each of the color channels. We place the LEDs in a honeycomb pattern to allow the light from the LEDs, which are point light sources, to cover the area more evenly. We then follow the electronic requirements of the LEDs to create the schematics and design the laser cuttable traces that allow the components to be placed in the honeycombs pattern. To fabricate the traces, we laser cut the copper mesh, which is weaved with copper thread with a fiber laser cutter. We then remove the excess copper and solder the LEDs. To achieve that, we use a laser cut stencil to apply the solder paste, We then manually pick and place the components and solder them with the hot plate. We then transfer the now functional circuit onto a textile substrate. To achieve this, we first put glue on the substrate. And use vinyl transfer tape to lift the circuit up and glue it on top of the chiffon substrate. The translucent chiffon substrate maximizes flexibility and allows the light to pass through layers. We repeat the process to make the UV layer, which is placed on top of the RGB layers made before. After making the LED layers, we take a look at the silicone diffusing layer. The silicone diffusing layer is made out of hexagonal unit with a hollow cone and tapered sides. They can be combined into a honeycomb pattern to cover the LEDs. Because the UV and RGB LEDs are not aligned, the distribution of saturation and desaturation don't naturally match. Therefore, the diffusing layer splits the UV lights from the UV LEDs to its neighboring pixels and avoids the saturation hotspot created by the UV light. With the RGB LEDs, it directs the lights so that the hotspot in the center of each pixel is mitigated. This allows the light from the UV and RGB LEDs to be aligned, enabling controllable color in each individual pixel. We made the silicone diffusing layer by casting clear silicone in SLA 3D printed molds. After the layers are fabricated, we then assemble them by sewing textile-based layers together with a sewing machine. And then we glue the diffusing layer onto the textile layers. Here is a small patch that we made following the process. We can also combine multiple patches to make a bigger one. For the applications, in addition to the backpack that we just presented, PortaChrome can also be attached to a wireless charger to allow reprogramming the back of a tablet case every time they charge the tablet. This turns the back of the tablet into a passive display that visualizes the progress towards the user's health goal. Similarly, PortaChrome can also be attached to the inside of a jacket sleeve to reprogram the user's splint brace underneath it to match the user's outfit. PortaChrome can also be a part of a product casing, such as a headphone case, to give the product a new pattern every time they're put back into the case. All of the color change mentioned above are completed within 4 minutes, which is 5 times faster than prior works. In summary, PortaChrome is a portable and flexible light source that can be attached to everyday object to reprogram the texture of multicolor photochromic material. In future work, we plan to improve the resolution through industrial electronic miniaturization and develop light sources with different technologies. We envision a future where color-changing materials of different kinds are used in our environment with custom devices optimizing for each material, scale, and interaction. Thank you very much for listening to our talk, and I'm happy to take any questions.
Hi, I'm Jotaro from Sony. Thank you for the great talk. It was great. I was also wanted to ask about the resolution. Really, I thought that it could be you could also like scan the photograph and then like if you could use the lens to kind of project the like imagery, like a camera, to kind of project the pictures onto photochromic material. Would that be possible?
Yes. Let me repeat your question to make sure I understand correctly. So, are you asking whether we can use a lens system to project an image onto a photochromic object so that it has more higher resolution?
Also, it's like kind of more like acts like a passive display, so you don't have to carry around like a LED, but you can use the natural source of light to kind of to render the pictures onto.
Oh, that's a really cool idea. So this kind of like goes back to the how photochromic works, because photochromic is a homogeneous material. So as long as you can create an image as long as you can create an image onto a photochromic material, the resolution of your image would be the resolution of the image that's left onto the photochromic material. I think one of the issues that you might run into if you do it this way is because if you harvest the light from the natural light, then the UV light, which is required to trigger the photochromic saturation, might not be there. So you probably need a way to kind of like create the UV light first and then use the natural light to desaturate. But it's a really good idea, and also technically you do have UV light in the natural environment.
Thank you very much.
Yeah, thank you.
Hi, Yunyi. Great talk. I'm Vivian from CMU. So it seemed like you made a panel, like a flexible LED panel that worked really well. And so for some of these real-time visualizations, I could see that you could just use the LED panel directly instead of the PortaChrome material. So I'm curious, as someone who's thought a lot about this, what are the pros and cons of using, for those kind of like real-time visualizations, like the tablet back as it charges, forming a heart? Why would you choose the use of one of the materials over the PortaChrome over like an LED panel?
This is an amazing question. Thank you so much. So the question is, why do we not just use a display? I agree there are different applications for display and for color changing material. In my opinion, one of the advantage of photochromic material is its scalability. So to make a display, you need the electronics on the back. You also need if you use LCD, the liquid crystal in the front, and sometimes if you use LED, it's a complicated device. But with photochromic, what we can do is that we can coat an object and make it and give it display capability. So one thing that we can do is that we can easily coat the entire wall and then just turn it into a very big display without having to have those like LED display panel. What we can also do is we can still have the look and feel of your object. So for example, you can have it on your t-shirt and still have your t-shirt be wearable. You can also put it on like a leather jacket and still have it feel leather. So you can basically give objects the display capability without changing the object. So I think that's...
Thank you.
Yeah.